So this is the first lecture on the topic of integration. So integration forms the second part on the course on calculus. The first part dealt with the topic of differentiation, which we learned earlier in the first part of the course on calculus. So before we go into the various aspects of integration in details, let us first of all recall what we learned in this on the subject of differentiation. That was the first part on the course on calculus. First thing, we learned that the equation of the straight line is y equal to mx plus c, where m is the slope of the straight line and c is the y-intercept. We are not interested in the c, the y-intercept. What we were interested in was the slope of the straight line. And we said that if a and b are 2 points that are x1 and y1 and b x2 and y2, the slope of the line, straight line, is defined as m equal to y2 minus y1 upon x2 minus x1. So that was very easy. Finding out the slope of a straight line was very easy. But what happens if we have to find out the slope of a curve? So if we have a point A, x1 and y1, let's say, and B, a point x2 and y2, say, okay. If we were to find out the slope of a curve at any point A, how will we do it? Okay, so suppose we draw a tangent at the point A, and the slope, because we define that the slope of a curve at any point is the slope of the tangent at that point A. So if we see that if we draw a tangent at the point A, let's say the slope is m1. If we draw a tangent at the point B, we have a slope which is m2. Just by seeing from the figure, we see that the slope m1 cannot be the same as the slope m2. So how are we going to find out the slope of a curve at any point A? We recall that we introduced the concept of limits to find out the slope of the curve at a particular point A. So if you recall, we said, let's say A is x1 and y1, and let's say B is x2 and y2. We started bringing this point closer and closer and closer towards the point A in order to get the slope of the tangent at the point A. If we can easily see that if we draw a line AB, we have a certain slope. Okay, if we again join A with this, the second point, the slope starts approaching the slope of the line at the point A if B is very close to A. So we introduce the concept of limits to find out the slope, that is m equal to dy by dx as limit of delta x tends to 0 equal to delta y by delta x, where delta y is the difference in delta y is a very small amount which is very close to the point A, and delta x is a very small amount on the x-axis very close to A. So if this delta x starts becoming 0, it approaches the slope of the tangent at the point A. That is what we learned about in differentiation. And from there onwards, by deriving from the first principles, we came to the point where dy by dx of any algebraic expression, A, if y is equal to ax to the power n, then dy by dx is n ax to the power n minus 1. We also found out differentiation of other expressions also, algebraic expressions. Then we came across trigonometric expressions, differentiation of trigonometric expressions, differentiation of logarithmic expressions, differentiation of exponential equations. Then we found out the differentiation applying the chain rule, the product rule, and the quotient rule. Okay, so this is what all we learned in the topic of differentiation in the course, the first part of a lecture on first course in calculus. Okay, so what is now integration? So in this first lecture, I am just going to let you into the concept of what integration is all about. Okay, so now let's understand what integration is all about. So let's see. This is the x-axis and this is the y-axis, right? Let's draw a curve. This is the curve. Let's take a point A on the curve, x1 and y1. Let's take a point B on the curve, x2 and y2. What is integration? Integration is the process of finding out the area under the curve. So if I take a point A and B and I find out that area under this curve, let's say it is the area A. So integration is the process of finding out the area under the curve between the points A and B. So if A and B are defined, it is known as definite integration. But if A and B are not defined, that means we don't know where the point A is. It can stretch this way or it can stretch in this way. We don't know where the points A and B are. That is called indefinite integration. So in this lecture, basically, I will just give you the concept of how to find out this area under the curve. So let's draw the curve again. This is the x-axis, this is the y-axis. This is the curve, okay? This is the point A, this is the point A. Let's understand the concept first. So if I have to find out the area under the curve A and B, I am interested in this area. Suppose I join A and B. Suppose I join A and B. Now you see, let me join the line A and B. Now, if you find that, if you see, this area is definitely less than the area, this area, right? So this is the extra area. Okay, this is the extra area. How are we going to find out now the area under the curve A and B? So it's like this. The concept is very, very simple. We are going to divide this whole area into rectangles. Let's start with dividing this into two rectangles. Let's say two rectangles. We divide it into two rectangles. Now, in order to find out this area, let's say this is one rectangle and this is another rectangle, right? This is another rectangle. But if you see this, if you find out the area of this rectangle and this rectangle, it is definitely more than the area under the curve by this amount, right? So we don't need this area. So if we are going to have two rectangles, this is the area which is extra. Let's see what happens when we divide this area under the curve into four rectangles. Now let's divide this into four rectangles and see what happens. Let's see what happens. Now, this is one rectangle. This is one rectangle. This is another rectangle. This is another rectangle. And this is the fourth rectangle. Now the extra area you will see is this one. Now, if you are going to add up these four areas, or from the total area of the rectangles, if you deduct these areas, we are going to get the area under the curve. So now we have four rectangles and we find that this area now is decreasing. What happens if we increase again? Let's increase the number of rectangles now. The same curve remains. This was four rectangles. Now let's divide this into, let's say, 8 rectangles. Okay, now again this. Okay, now you see again, this is the extra area. This is the area which is extra. This is the area which is extra, right? So again, if you were to add up all these extra areas, you will find now that it is still less than the area that we had before. So now the concept is becoming very clear that as we go on increasing the number of rectangles, if we go on increasing the number of rectangles, the area will start, see, let's say 12, then we 100 rectangles, 1000 rectangles, let's say 10,000 rectangles. Suppose we started with the extra area, say something like 100. If we were to calculate these extra areas, let's say with 4 rectangles, this would have decreased to 80, and so on until it finally tends towards 0. So again we have to understand now again the concept of limits will be coming in, where we will be summing up the area of all these rectangles, and this sum, after finding out this sum and finding out the sum for a huge number of rectangles, which is approaching infinity. So as these number of rectangles approach infinity, we will find that the area under the curve will approximate to the area under the the sum of the area of rectangles will approximate the area under the curve AB. Okay, so this in short is the concept of finding out the area under the curve A and B. So in the next lecture, we will go into finding out the area of these rectangles. We'll go into the concept of finding out the area of the rectangles and some of the area under the rectangles when n is tending towards infinity. This summation we will be taking in the next lecture, and you will find that after summing up all this area under the rectangles, we will approach towards the general formula for integration for algebraic expressions. Okay, this is all for this lecture. Thank you.